I'm Roshan. I work at Samsung in the Global Open Ecosystem team. And today I'll be talking about NVMe FDP and what it can do if you're looking at data center sustainability. So thank you all for being here. And a big thanks to Dan, because he covered all the FDP stuff on the device side. I'm going to talk about how you can use FDP from the host and what that means for data center sustainability. So I'll start with a quick motivation on why have this talk at all, right? Why talk about FDP in the context of sustainability? And then we'll go over a bit of background on what we mean by storage sustainability, right? Amplification, SSD lifetime, and power. And then we'll get into FDP and how you can use FDP to reduce your carbon emissions. We'll go over a few examples with FIO. And finally, we'll talk about CacheLib. I think Dan gave a small glimpse into the data. We'll go a lot deeper into it here. So let's get started, right? So why have this session at all? What is the motivation behind having this? I think a lot of the companies that we work for have promised to achieve net zero carbon emission goals sometime in the next 2 decades. And as a part of being able to achieve this promise is to invest in technologies and research technologies that can actually help you reduce carbon emissions. And I think data centers are only growing in number and size. And data center carbon emissions are set to go through the roof, right? And SSDs do have a very sizable contribution to the data center carbon footprint. And we're at a time now where, if you see, we're starting to adopt QLC SSDs. And one of the use cases is to eventually replace hard disks with SSDs. But I think we all know that for more than one reason, it's not as simple as just take your hard disks out, put your QLC SSDs in, and everything's great. And one of those reasons is that SSDs do have a higher carbon footprint than hard drives. And so we'll talk about that a bit here. And last but not the least, for me personally, I think as an engineer and a developer that works on FDP, I was able to make the connection between FDP and sustainability. And being here at SDC, I saw a lot of people talking about a lot of technologies that can actually help sustainability, but haven't really made that connection. So for me, it would be a win if at the end of this presentation, a lot more people start talking about sustainability in their KPIs. So what do we really mean by storage sustainability, right? So maybe a lot of you already know about it, maybe some of you don't, but this is mostly to set the context for the rest of the presentation. So like I said, a lot of companies have promised to achieve net zero carbon emission goals. And the way they're being held accountable to that promise is by releasing sustainability reports every year. And if you go and look at those sustainability reports, they report on their carbon footprint in these 3 categories: scope 1, 2, and 3 carbon emissions. And in this slide, I'll just define these things, and quickly we'll go into how these relate to SSD metrics and parameters. So scope 1 carbon emissions are those that come from direct burn of fuel, right? So if you're actually burning coal or fuel to run your equipment on site, that would come under scope 1 carbon emissions. But most of us don't actually do that. So which is why typically scope 1 carbon emissions have a very low contribution to your total carbon footprint. And so we're not going to talk about it in this talk. Scope 2 carbon emissions are also called indirect carbon emissions. And this is essentially when you purchase energy or power to run your equipment. So in a data center, you have servers, SSDs, all of this. And also because you're purchasing energy to operate your hardware, this is called operational carbon emissions. And this is a term I'll use repeatedly throughout the presentation. So maybe, it'd be good if you could remember that. Typically, operational carbon emissions do have a sizable contribution to a company's carbon footprint. And if you talk to any sustainability expert out here, they'll tell you the way to solve for operational carbon emissions is to move to renewable energy. But we all know that's some time away. So we will talk about how you can optimize operational carbon emissions in this talk. You could basically think of operational carbon emissions as the power your SSD consumes. That's the correlation, for this talk at least. And last but not the least, scope 3 carbon emissions. These are called embodied carbon emissions. And the way to think about this is during your SSD manufacturing process, a lot of greenhouse gases are released, which is now kind of embedded or embodied in that SSD that has been manufactured. So if you're purchasing SSDs, you are responsible for that carbon footprint. And every SSD has an inherent embodied carbon footprint attached to it. So if you are building a data center and you're buying more and more SSDs, your embodied carbon footprint will kind of add up. Right? So the way to think about it for this talk is embodied carbon emissions is related to lifetime of your SSD. Right? So these are the kind of categories of carbon emissions, but how do you quantify it? Very quickly, we use a metric called CO2e, carbon dioxide equivalent, which essentially means that every greenhouse gas has an equivalent conversion to carbon dioxide. So you just convert it and report just the CO2e value. So in the context of operational carbon emissions or power consumption, what that means is if you can estimate over your system's life cycle how much power your SSD is consuming, so you'd get a kilowatt hour value, you could convert it into an equivalent carbon footprint using various calculators available. So these calculators are released by the governments and they depend and vary based on regions. The one I've linked here is for the US. And if you think about it for embodied carbon emissions, there's a well-studied, well-documented paper in the academic world where they actually went and looked at a bunch of SSDs and kind of tried to estimate what the carbon footprint is if you're buying an SSD. And the value they came up with was 0.16 kilogram of CO2e. So what that essentially means is if you're buying a 100 GB SSD, you're responsible for 16 kilograms of carbon emissions. And if you're buying 2 such SSDs, you'd be responsible for 32 kilograms of carbon emissions, and so on and so forth. So with this little bit of context in mind, what you should remember is just operational carbon emissions and embodied carbon emissions. The rest is all fine. So what does that mean to us if you're building a system? So let's say you're building a system. The first thing you try to do from the storage perspective is you try to forecast how much GB of SSD capacity you'd need for your system. You'd also try to account for premature SSD failure for whatever reason. And then you'd kind of figure out over your system's life cycle, how many SSDs will you purchase, right? So throughout the talk, we assume the system life cycle period is 5 years. It doesn't matter. It could be anything. Just, you could adjust your calculations accordingly. So if you end up with this estimate of how much GB of SSD you are actually going to purchase over your system lifecycle period and multiply it with this 0.16 kilogram of CO2e value, you end up with what we call the capital carbon expenditure, which is essentially how much carbon you're paying upfront for your system to build your system. And obviously you bought SSDs, now you're going to operate them, so you're going to need power or energy. So if you're able to estimate over your 5-year system lifecycle period how much energy you're spending to run these SSDs, you'd end up with the operational carbon expenditure. So the sum of these two gives you, for a system, the total carbon cost of ownership, which we call TCCO here. This might sound very similar to TCO, which is your total cost of ownership in terms of dollars. And the reason I kind of put this small graphic here is to point out that optimizing for total cost of ownership and total carbon cost of ownership might be diverging goals. They might not always mean you're optimizing for the same factors. So with that context, what does that mean to an SSD and SSD metrics? So we all know that right amplification factor is kind of a proxy measure for endurance of SSDs. So if your WAF is high, it means your SSD lifetime is going to be lower. So taking an example, if your WAF is 3, it would mean that your SSD would last for a third of the lifetime that it would if your WAF was 1. And obviously this means if you're building a system and you want your SSD to last for some amount of time, so 5 years throughout this presentation, but your WAF is 3, it means that you'll have to buy more SSDs to replace your failed SSDs, which essentially means that you're going to have a higher total cost of ownership because you're spending more money to buy those SSDs. And also it means from the discussion till now that every SSD you buy has a carbon cost attached to it, so your carbon cost adds up as well. And so you're going to end up having a very high embodied carbon footprint. That's the key. So obviously the way to make sure that your system is more carbon efficient is to make your SSD last longer. And the way to do that is to control WAF. And one common method used by a lot of people is host over provisioning, which is they buy an SSD and only use some of it, so they underutilize the SSD. And this is inherently inefficient for various reasons and also for carbon emission reasons because you're paying all this carbon to buy a huge SSD, but you're only using some of it. So throughout this presentation, we'll cover why host over provisioning is a very bad method and data placement is a much better method to save carbon. And for this presentation, I used a Samsung drive, which is FDP enabled, but none of the embodied carbon emissions are for this drive because we're using an averaged out academic researched value. So now that we know that if your WAF is high, your lifetime is low, so you have to buy more SSDs, your embodied carbon footprint is high, what does a high WAF mean for power consumption and operational carbon emissions? So if you think about it, when do you get a high WAF? You get a high WAF if your SSD is doing some extra internal stuff inside, like garbage collection. So for a fixed host workload, if your WAF is high, it means the SSD is doing additional reads and writes in the form of garbage collection. So that essentially translates to a higher power consumption. So too long didn't read, your WAF is high, your power consumption is high due to the extra garbage collection events. If your power consumption is high, your operational carbon emissions are going to be high as well, right? So the key here is that, again, the way to reduce your operational carbon footprint or reduce your power consumption is to make your SSD WAF lower. And again, we believe that data placement is a good way to do it, which we'll cover throughout this presentation. This is a small graph to illustrate this impact. So if you look at the graph here, I've run an FIO sequential and random workload over 5 hours. And I've made sure that for both workloads, the total writes that the host do is fixed. So if you look at the blue line, the solid blue line, that's your SSD WAF for sequential. And the solid pink line is your SSD WAF for the random case. And the dotted lines are power consumption. So if you look at the solid blue line, you can see that the WAF stays 1 throughout because it's a sequential write. That's what you'd expect. And also if you see the power, the dotted blue line, you can see that there aren't too many variations and the power is kind of constant. And in this case, it was 6 watts. But now if you look at the random write case, initially the WAF was 1 till your SSD got full. And as your SSD started getting overwritten, you can see that the WAF goes very high, all the way up to 4 roughly. And you can see that the SSD power has a similar trend. So the point I want to drive through this example is that if you're able to keep your WAF low, your SSD power consumption will stay low and constant as well. But if your WAF goes high, your power will follow a similar trend where your power consumption goes high as well. Now, we did speak about one method to control WAF, which is over-provisioning. And I'll spend a couple of slides talking about over-provisioning and what it means for reducing your WAF and also why it's a bad method to reduce your WAF. So if you look at the graph here on the right-hand side, on the x-axis, we have varying levels of device utilization. And the purple line here is your SSD WAF. And the blue kind of curve with the cross marks is your embodied carbon emissions. So remember, embodied carbon emissions are attached with SSD purchase. So you would assume that if your WAF is low, everything's great. Except if you look at the first data point, which is 25% device utilization, you see that the WAF is 1.3, right? Because you're only using 1/4 of your SSD. The rest is just free for your SSD internally to cushion garbage collection. But you see that the embodied carbon emissions are highest for 25%. Why is that, right? Because you're buying all this SSD capacity and not using it. You're just wasting it. So the carbon cost you pay is very high for 25%. And the best carbon cost in this example is for 75% device utilization. While the WAF is 1.7 there, which means your SSD is degrading 1.7 times faster than it would otherwise, you're also wasting not as much space. You're wasting 25% space. So the key here is that yes, over-provisioning does, like host over-provisioning does help you reduce WAF, but it's not the best way to do it because you're wasting a lot of space by trying to reduce your WAF through over-provisioning. And what does it mean for SSD power? In this table, I've kind of summarized the previous graph where I've just listed down the WAF values for various device utilization. The graph here is kind of similar where you have device utilization on the x-axis. The purple line is your SSD power consumption, and the black line with the cross marks are your operational carbon emissions. Here it's a bit more straightforward because if your WAF is low, like we discussed, it means there's no GC kicking in your SSD, which means you don't have additional read and write operations happening in your SSD, and so your power consumption will be lower. And so you would expect that as your device utilization increases and your WAF increases, your SSD power and carbon emissions would increase, which is what you see. But the interesting thing here is if you see the point or the device utilization at which you get the least operational carbon emissions, it's 25% device utilization. But in the previous slide, we saw that 75% device utilization is where you get the least embodied carbon emissions. So which one do you optimize for? Do you optimize for SSD lifetime or SSD power, right? That's kind of the question here. And if you look at the actual values, which I've put in the box in red text, the operational carbon emissions are roughly 150 kilogram of CO2e, but the embodied carbon emissions are 750 kilogram of CO2e, which means that your embodied carbon emissions have a much higher magnitude than your operational carbon emissions. And if you go back to our table here, that's what we said, right? The embodied carbon emissions are much higher than your operational carbon emissions. So we kind of just confirmed that using this example. But the main point here is that if you use over-provisioning to control your WOF, you're left with a question of optimizing either operational carbon emissions or embodied carbon emissions and not both, right? So that's a pretty bad method. So what are our takeaways so far, right, with all this background? It's essentially that SSD WOF affects both operational carbon emissions, power, embodied carbon emissions, lifetime, and reducing WOF helps you reduce your overall system's carbon footprint. And embodied carbon emissions are larger in magnitude than operational carbon emissions. So if you had to optimize for one, you would pick embodied carbon emissions. So with that in mind, let's move to data placement, which we believe is a much better method of optimizing and reducing WOF, and therefore also carbon emissions. So in specific in this talk, I'll talk about NVMe FDP. I'm not going to get into FDP versus other data placement technologies here. So I'm assuming everyone knows about FDP, but in case you don't, this is a quick one-slider. So if you look at the right-hand side, the image on top kind of depicts a conventional SSD case from the host perspective. You have no means to segregate your different data types when you write to the SSD. So in your SSD, all your different data types kind of get mixed together, and that's inherently bad for your WOF. So you'll end up getting a high write amplification factor. And if you do, from our discussion so far, your SSD power will be high, and your SSD lifetime will be lower. So your carbon footprint will be higher. The image below is the host perspective when you are able to use NVMe FDP. So you're able to segregate out your different data types when you write into your SSD. And that's nice because most times different data types have different write patterns or overwrite patterns, and that means your invalidation in your SSD is going to be good, and so your write amplification will reduce, which we'll illustrate through examples. So what that means is, what using FDP essentially means is you have a means to reduce your write amplification factor, which means you're able to improve SSD lifetime and reduce SSD power, which, like we discussed till now, means you're able to reduce your system's carbon footprint. I think the key here is that FDP is very easy to adopt from the host perspective. You don't need major application changes in adopting FDP, which typically is a no-go most of the time. And also FDP helps reduce over-provisioning, which again I'll illustrate through examples. I just want to take a second to point out here that I've kind of linked to a few white papers that we've released at Samsung. So if you're interested in FDP at all, make sure to check that out. So what does using FDP mean for carbon emissions, which has been our discussion till now, right? So what does it mean for write amplification and therefore carbon emissions? So the first example that I'll use to illustrate FDP's impact is, again using FIO, where I have two streams of data, both sequential, but both writing at different rates. And you'd assume that if both sequential writes would mean that you can still achieve a low WOF without data placement, but nope. If you look at the graph, the line in blue is the FDP WOF. You're able to achieve a WOF of 1. Whereas without data placement, even though you have sequential writes happening to the drive, the different write rates result in the WOF going high, and your WOF goes to roughly 1.4. So what does that mean for carbon emissions, which is our discussion here? So if you look at the bar graphs, if your non-FDP SSD were to last for a year, in relative terms, your FDP SSD would last for 1.35 years, which is pretty nice. And if your non-FDP SSD would emit 1 unit of carbon relatively, your FDP SSD would only emit 0.75, which is a 25% reduction right there, just for free, right? By just tagging your data. So I think that is the power of FDP, and we'll look at more examples, of course. And the key here is that sequential writes don't always mean that everything's good for your SSD. Sometimes you still need to segregate your different sequential writes out. Now, what does it mean for SSD power? So if you look at the power consumption here, with non-FDP, because the WOF went high to 1.4 roughly, your power consumption goes high to 8.7 watts in this example. Whereas with FDP, you're able to maintain kind of a nice power consumption of 7 watts. So this is a very direct reduction in power consumption by using FDP. But the most interesting metric to me at least is if you look at the table, the third column kind of highlights the number of garbage collection events that occurred during this example. And this was pretty nice. We used the FDP event log to collect this. So what we observed is that with FDP, over this 5-hour run period, you had only 2 garbage collection events. But without the data segregation, you had 8,150 garbage collection events. And this is directly reflected in the graph, because if you have more garbage collection events, your SSD power will be higher. But to me, this was the most interesting metric, that FDP, which we expect to happen, should reduce garbage collection events, and we confirmed that. So let's look at a slightly more complicated example now. So here we have 4 streams of data, 2 sequential streams writing 45% of your LBA space, and 2 random streams each writing 5% of your LBA space, right? So overall, it's kind of 90% random and 10% sequential. So again, a small amount of random write. If you look at the graph here in pink, it's the non-FDP WOF. The WOF goes all the way to 3, but with FDP, you're able to get a WOF of 1.1. So again, here you see that data segregation helped you almost for free to get a very low WOF. You didn't do any major changes. You just tagged your different data types, and you're able to get a WOF of 1.1. And here the impact on carbon emissions are even higher, because if you look at the lifetime, if your non-FDP device were to last for a year, your FDP device would last for 2.5 years, which is like a massive gain. And if your embodied carbon emissions with non-FDP were going to be 1 unit, you'd have a 60% reduction in that. So again, for free, you got a 60% reduction in your carbon footprint, right? So this translated to SSD power. Again here, the garbage collection events are the most interesting kind of parameter. When you had 4 streams, 2 sequential, 2 random, 10% of random, right? We saw that with FDP, you had 3,700 garbage collection events. Whereas without the data segregation or data placement, you had 12,240 garbage collection events. And that's reflected in the power consumption as well, right? So the non-FDP power is 34% higher. So again, for free, you got a 35% reduction in SSD power consumption. So all of this is nice. These are FIO examples, synthetic, made up, but does it actually work in a real system? And that's what I'll try to answer now. So we've essentially integrated flexible data placement to CacheLib. And this is just a context of what CacheLib is so that we can follow the rest of the data presented. So CacheLib is an open source hybrid cache that was developed and is maintained by Meta. So, like I said, there's a DRAM cache and a flash cache stacked on top of each other. And we're interested in the flash cache because that's where the SSD sits. So CacheLib's flash cache has 2 caching engines in the purple and the blue, block cache and big hash. Your larger caching items will go into block cache typically, and your smaller caching items will go into big hash. So block cache has a log structured write to your SSD, which essentially results in sequential writes, which we know is good for the SSD. Big hash is a set associative cache. Essentially, it's a hashing function going on, so you end up getting random writes. And typically, those random writes are 4 KB, right? So we know that that's kind of the worst case scenario for your SSD. And here what happens typically is that this data gets mixed when you write to the SSD because you have no way to segregate it. And CacheLib has observed, like, in their deployments, they observed that if you used the entire SSD, so if you bought a 2 TB SSD, for example, and used all of it for your flash cache, you'd end up with a WOF of 3.5, which was unacceptable for Meta in its deployments. So the way they kind of dealt with it is they're like, okay, we don't want to solve this problem. Let's just use half our SSD. So they over-provisioned the SSD, and so they buy a 2 TB SSD, but use only half of it. And even then, they're only able to achieve a WOF of 1.1, not lower. So this is where we felt that there's an opportunity to use FDP because block cache and big hash inherently have different data characteristics. One is sequential write and kind of infrequent. One is random write and very frequent. A little bit more context about the deployment scenarios before I get into FDP is CacheLib's production deployments typically use 43 GB for their DRAM cache, and they usually buy a 2 TB SSD and use half of it for their flash cache. And in the flash cache, typically your block cache, the sequential write will be 96% of the LBA space, and only 4% is random writes, right? And even then you see that when you use the entire SSD, just 4% of random writes was enough to cause a WOF of 3.5, which is pretty drastic. And the workload we used throughout this presentation for the remaining graphs to benchmark CacheLib is the KV cache workload. which is a popular workload at Meta's CacheLib, and it's been open sourced, so the traces were available. It represented a fairly production-like scenario, which is why we used it. So with KV cache, like I said, when Meta used their entire SSD, they'd get a WAF of 3.5. So their solution was to just over-provision it, and then they achieved a WAF of 1.3. Interestingly, when CacheLib released their paper in OSDI, there's a line in the paper which essentially admits that they have no clue how to improve the WAF and improve the device utilization without affecting their CacheLib KPIs. And so it was kind of like an open challenge or an open problem to solve. And that's where we used FDP. So what does FDP help you do, right? So FDP helps you, like I said, segregate out your block cache and your big hash writes to the SSD. Just a reminder, your block cache is your sequential write and infrequent updates. Big hash is your random writes and frequent updates. So with FDP, it's as simple as just segregating these out when you write it into the SSD. And we observed that just doing that meant even if you use your entire SSD, you're able to achieve a WAF of 1, which we thought was pretty impressive. And just to give some more context, we have a paper regarding this that's been accepted to Eurosys, which I have kind of linked below. So do check that out if you're interested at all. And what did these gains mean for us, right? So it meant that if you're able to reduce your WAF, obviously from CacheLib's perspective, you're able to use more of your SSD. Initially, they were using only 50% of their SSD, but now they can use the entire SSD without affecting their KPIs. But also it meant that because CacheLib clusters are thousands of nodes and there are thousands of clusters as well, it means that this reduction in WAF resulted in a reduction of power, which was pretty good for them. They liked that. And also it means that your SSDs last longer, so you need to purchase less SSDs. That's kind of the too long didn't read. But the graphs here, kind of showcase this in a bit more detail. So the first graph on your left-hand side is CacheLib when, in the default case, when 50% of the SSD is being over-provisioned, like not used. And the second graph here on the right-hand side is when you're using CacheLib with the entire SSD being used. Again, the pink line is non-FDP and the blue line is FDP. So I think the gains are pretty obvious to see. With FDP, you get a WAF of 1, doesn't change. But without FDP, which was the default case, like we said, the WAF hovered around 3.5. And obviously, these have massive implications to SSD lifetime and embodied carbon emissions. So it obviously means that if your SSD lasts longer, you need to buy less SSDs, like we said. So that's captured in the table here. I think the main thing to think about here is not just that the WAF stayed at 1, but it also means that now for caching, you have 50% more space to cache data, which also means that you have roughly 1 TB of extra space to cache your important data for your workloads. So that does have trickle-down implications with respect to how you can configure your DRAM. And as we know, DRAM is a lot more expensive than flash, and I'll cover that in a couple of slides. So what did this mean for power consumption, right? So the first 2 rows here are with the KV cache workload, which I described, which is the characteristics of the KV cache workload are 80% gets and 20% sets. So it's read intensive. So even with the read intensive workload with FDP, you can get roughly a 0.5% reduction in power consumption, which if you amplify over the 1000 node CacheLib cluster and lots of CacheLib clusters again is pretty massive. But we tried to make the scenario even worse, right? So we tried to run a write-only KV cache workload, which was 100% writes, and we're like, okay, let's see how good or bad it gets. Even with the write-only KV cache workload, where you have 100% writes, FDP gives you a WAF of 1. And now the power reductions are even more impressive, and you have a 30% reduction in power consumption, which directly means you have a 30% reduction in operational carbon emissions. And the key I want to point out here is we used FDP to do data placement and reduce WAF. And here you didn't have the same problem that you did with over-provisioning. You didn't have to pick between optimizing operational carbon emissions and embodied carbon emissions. You were able to optimize both without having to prioritize one or the other, which again is pretty sweet. So like I said, the increase in your SSD utilization has an impact on, or it gives you the ability now to deploy CacheLib in a more flexible way, which we also believe is a very nice benefit of using FDP. So this table kind of summarizes the various configurations used for the RAM cache size. So we use a 2 TB SSD for the flash cache, and we use 100% of the SSD, no over provisioning. And we vary the DRAM configurations. So like I mentioned earlier, the default that CacheLib uses is 43 GB of DRAM. So we try to reduce that and see what happens in CacheLib, right? So the key to note here is that the SSD write amplification that you get when using CacheLib the DRAM has no impact on that. It doesn't matter. So for all of these configurations, with FDP, you get a write amplification of 1. Whereas with non-FDP, your write amplification is 3.5 because you're using your entire SSD, right? So the key motivation to do this was 2 reasons. One is DRAM is more expensive, and DRAM also has a higher embodied carbon footprint. So this is another way in which like large-scale deployments can optimize their carbon footprint. So the conclusion of our experiment where we varied DRAM was, if you look at the last row and the first row, the last row is kind of the best case without FDP, and the first row is kind of the worst case with FDP. And even then you see, yes, we do get a 30% reduction in throughput, because now instead of your DRAM serving your sets and gets from your cache, they have to now go to your SSD to retrieve the data. So you will see a reduction in throughput, which was 30% in this case. But you also saw a 70% reduction in carbon footprint. Now, with the ambitious carbon emission goals that exist, that a lot of companies have set out to achieve, this is pretty interesting, because if you vary your DRAM in CacheLib in specific, you're able to reduce a lot of your carbon footprint. And I think the key to note here is, without FDP, such an exercise of even varying DRAM was not possible, because you'd have such a high SSD WOF that your SSD would just burn through really fast. So this kind of deployment flexibility was only afforded due to FDP's ability to keep your SSD WOF low and improve device utilization. So that's kind of all I wanted to talk about. So I'll kind of summarize our key discussion points for this presentation. So NVMe FDP helps reduce SSD WOF, as we know. But these have trickle-down effects in helping you reduce your embodied and operational carbon emissions almost for free. You don't have to pick between the two like we did for over-provisioning. And moreover, NVMe FDP helps you reduce host over-provisioning. Like we saw with CacheLib, you can now use your entire SSD to cache data. You don't need to save some of that to cushion your WOF. And again, this has impacts on carbon emission, because you're not buying an SSD and wasting it. You're buying an SSD and using all of it. And last but not the least, FDP has the ability to provide deployment flexibility. Because your SSD can be used in its entirety, and you still, in this case with CacheLib, you didn't have an impact on WOF, you are able to optimize your DRAM configuration, which means you needed less DRAM. And that means, again, that's another way in which you could optimize your system's carbon emissions. So overall, we compared over-provisioning and FDP in this presentation for data placement, and we saw that over-provisioning is not the best way because it's wasteful, and FDP achieves what we intend it to do, which is get an ideal WOF of 1. That's all I had. So thank you, and if there are any questions, I'd like to answer them. So could you be a little louder? Yeah.
Who modified CacheLib to add FDP support?
Okay, yeah. So the question is, who modified CacheLib to add FDP support? So we in Samsung, in the global open ecosystem team, we collaborated with Meta's team that ran CacheLib, and we actually upstreamed the support to use FDP in CacheLib. So yeah. So now that is upstream and available in CacheLib. And you can find more details about it in the user guide in CacheLib, which talks about the FDP support that we added. Yeah, I think it was a collaboration, so it was not very difficult to do. I think both parties wanted to do it, so yeah, we were able to achieve it pretty easily. Yeah.
Do you know how long it took?
Yeah, it did take us some time, but mostly because while we tried to upstream our code, there was some code refactoring going on in CacheLib, so we had to resubmit our PR for it. But yeah, it took a good chunk of time, I'd say like 6 months or so, yeah. Okay, if there's nothing else, Yep, thank you.